Hello, this is the section 7.2 lesson. For this lesson you're going to need your calculator and table A2. In this section we're going to start talking about some topics that would fall into the category of inferential statistics. In inferential statistics, that's where we use information from a sample to make conclusions about a population. Or stated another way, we use some statistics that get from a sample to make some conclusions about a population parameter. Okay? So to illustrate this, let's look at this example. Suppose we want to know the proportion of all college students that use credit cards. Now remember we said back in chapter 1 that a proportion is the same as a percentage. Just proportion is the decimal equivalent of a percentage. So in order to calculate this number exactly, I would have to go out and ask every single college student, do you use credit cards? I have to take the number that do use credit cards and then divide it by the total number of college students that I talk to. Now this number P, this population proportion P, is a parameter because it would be calculated based off information from every single member of the population. However, that number would be very difficult, if not impossible, to obtain. Again, because it would require me to talk to every single college student across the nation, which is very difficult, if not impossible, to do. So instead of calculating exactly, we're going to talk to a sample of college students. So the Education and Resource Institute randomly selected 750 college students and found that 480 of them use credit cards. So based off of that, we would calculate a sample proportion denoted by P hat, take the number that do use it, divide 480, divide it by the total number that we talked to, 750, and we would get 0.64. So there we have a sample proportion of 0.64. That number is a statistic because it was calculated based off information from a sample. Now this statistic of 0.64 is an estimate of our population proportion P, which is what I really want to know. This is what we call a point estimate of P because it is simply a one number estimate of P. Well, whenever we estimate something, we want to get a measure of its accuracy. So how accurate is this estimate? And we're going to answer it in a couple of ways. First of all, we're going to calculate the margin of error, which is a measure of its accuracy. And then second, based off that margin of error, we're going to calculate what we call a confidence interval, which is going to be a range of possible values for P as opposed to just a one number estimate. Now this idea of a confidence interval and margin of error are ideas that you may be familiar with from normal everyday life. You maybe don't call them these things, but hopefully you're somewhat familiar with them. Well, before we start calculating margin of errors, we need to talk about a concept that we've mentioned before we call critical values. We first mentioned this term critical value back in chapter 10. And here we're going to start using critical values for different purposes. So when we start doing topics in inferential statistics, we first have to choose what we call a confidence level, which is a measure of how confident we want to be in our results. Now a confidence level can range anywhere from 1% up to 99%. Three of the most commonly used confidence levels are given here: 90%, 95%, and 99%. Associated with each confidence level, we have a value called sigma, or denoted sigma, which is called the significance level. And this significance level is simply 1 minus the decimal equivalent of the confidence level. So for 90% alpha is 0.1, 95 it's 0.05, and 99% is 0.01. Now for each one of these confidence levels, we have a critical value, which is denoted z sub alpha divided by 2. It's called z because it is a z-score. We'll talk about the subscript alpha divided by 2 here in a minute. But for 90%, the critical value is 1.645, etc. Okay. Now on table A2, if you look at the positive z-score side, down in the bottom right-hand corner, you see this table labeled common critical values. And that's just the same table that we had on the previous slide, except they don't give the significance level. These are called common because these are not the only confidence levels that we could use. So you don't have to memorize these critical values. They're right there on your table A2. Now let's talk about this subscript alpha divided by 2, where it comes from, and a little bit about how these critical values are calculated. So suppose we're working at a 95% confidence level. So alpha is 0.05, which means that alpha divided by 2 is 0.025. Now the critical value for 95% confidence level is 1.96. Well, if I look on my z-score table, the area to the left of negative 1.96 is 0.025. That's alpha divided by 2. So that's where the subscript alpha divided by 2 comes from. Z sub alpha divided by 2 is a z-score for which the negative value of that, the area to the left, is alpha divided by 2. Now by symmetry, the area to the right of positive 1.96 is also alpha divided by 2, 0.025. So the total area of the red shaded region is going to be 0.05, which is alpha. That means the area in between the negative z-score and the positive z-score is going to be 0.95, which is our confidence level. So that's how these z-scores are calculated. Z at the 95% level, the area between the positive critical value and the negative critical value is 0.95. If I were working at a 90% confidence level, the area between the positive critical value and the negative critical value is 0.90. So now, using these critical values, we can calculate our margin of error. So I first need, let's let p hat equal our sample proportion. That always comes from the data. Next, q hat is 1 minus p hat. This is very similar to what we saw with the binomial distribution, where q was 1 minus p. N is our sample size. Again, that comes from the data that we selected. So then our formula for margin of error, E, is equal to z sub alpha divided by 2, which is our critical value, times the square root p hat q hat divided by n. So this is a fairly simple formula for the margin of error. So let's look at our first example of using this. We're going to use this data about the number of students that use credit cards. Let's find the margin of error corresponding to the 90% confidence level. Okay. So here's our formula. And our numbers, p hat is 0.64. Remember, that comes from our sample data. Q hat is 1 minus 0.64 or 0.36, excuse me. And n is 750. That's our sample size. Okay. The only other thing we need is our critical value, which comes from our table. So 90% critical value is 1.645. So now we plug things into our formula. Now 1.645 times the square root 0.64, 0.36 divided by 750. There on the right you see the calculator commands. And note that we can enter this in one big step. We don't have to break it down into several small steps. And we see our margin of error, 0.0288. Okay. Now, what does this mean? What does this margin of error mean? We would interpret this by saying we are 90% confident that the difference between the true population proportion p and the sample proportion p hat is no more than 0.0288. So this margin of error is like a largest difference between our actual population proportion and our sample proportion. Well, now let's do the same thing but work at the 95% confidence level. So the formula is the same. The numbers p hat, q hat, and n are the same. The only thing that's different is our critical value. Here we'd use z sub alpha divided by 2 is 1.96. And so I plug things in. Notice that what's underneath the square root is identical to what we did before. The only difference is the critical value out in front. And so here's our margin of error, 0.0344. So this one we would interpret by saying we are 95% confident that the difference between the true population proportion and our sample proportion is no greater than 0.0344. Notice this is a little bit bigger margin of error than at the 90% level. So if we want to be more confident in our results, we give ourselves a larger margin of error. Okay, so we just calculated the margin of error at the 90% level and the 95% confidence level. Next thing we want to calculate is what we call our confidence interval. Confidence interval is going to be a range of possible values for p as opposed to just a single numerical estimate of it. And the confidence interval is going to take one of three different forms. This first form is the one that we'll use in our calculations and that Course Compass uses. The second one is one that's used in the news media frequently, and the third one is used by your calculator. So in the first form, we calculate confidence interval by taking p hat minus e, and that's less than p, which is less than p hat plus e. So this p hat minus e is what we call the lower confidence interval limit. P hat plus e is what we call the upper confidence interval limit. Again, it's a range of possible values. It's saying that p, or population proportion, is somewhere in between those two numbers. The third form is very similar to that first form, except it uses interval notation rather than inequality notation. The second form is what's often used in the news media, specifically when they give polling results from like an election. So they might say something like 55% support this candidate with a margin of error plus or minus 4%. So their E would be 4% or 0.04, P hat would be 55% or 0.5. Okay. So using this formula is very simple. Let's find the 90% confidence interval estimate of the population proportion P. So there's our formula. Now all we need to do is plug in our numbers. P hat is 0.64, that comes from our data. E is 0.0288, that was our margin of error at the 90% confidence level. So do 0.64 minus 0.0288 is the lower limit. The upper limit is 0.64 plus 0.0288. We do that arithmetic, we get 0.611 is less than P is less than 0.668. So again, we have a range of possible values for P as opposed to just a single number estimate. Okay. Now let's talk about interpreting this confidence interval. A correct way to interpret this would be to say that we are 90% confident that the true population proportion P is somewhere between 0.611 and 0.669. Or 90% confident that P is somewhere between those two values. An incorrect way to interpret this would be to say that there is a 90% chance that the true value of P is between 0.611 and 0.669. Now at first glance these two statements look very much similar to each other, but what's incorrect about the second one is that there's no probability involved. P is either in the interval or not. There's no probability involved. Once I've calculated the interval, P, which is a single number, is either in that interval or it's not. There's no probability involved. The analogy that the book gives is like if a baby has just been born and the father comes out of the delivery room and people ask, well, is it a boy or a girl? And well, the father could say, well, there's a 50% chance it's a boy and a 50% chance it's a girl. Well, no, that doesn't really make any sense because it's either a boy or a girl. That's already been determined. There's no probability involved. Just tell us what the gender is, either a boy or girl. Just tell us. Same thing here. P is either in that interval or it's not. There's no probability involved. Okay. So again, here's the correct interpretation. We're 90% confident that P is between those two numbers. Now, next thing you might ask is, what does this number 90% mean then? Well, this means that if we were to select many different samples of 750 students and construct the corresponding confidence intervals, 90% of those intervals would actually contain the true value of P. So the 90% refers to the process of constructing the intervals, not the intervals themselves. Once the intervals are constructed, P is either in there or it's not. But if I were to construct a whole bunch of different intervals, 90% of those intervals would contain the true value of P. That's what the 90% number means. Now if we were working at the 99% confidence level, then 99% of our confidence intervals would contain the true value of P. But that's what the confidence level means. Well, now let's do the same thing, do a confidence interval, but work at the 95% level. Now the formula is the same. P hat is the same, 0.64, but now we need to use the margin of error corresponding to the 95% confidence level, which we calculated to be 0.0344. So if I do that arithmetic, I get my confidence level. P is somewhere between 0.606 and 0.674. Okay. Now let's make an observation here. At the 90% level, we said P is between 0.611 and 0.668. The 95% level, we're 95% confident that P is between 0.606 and 0.674. So notice that the 90% level, we have a wider confidence interval. We have a bigger range of values. And so a higher confidence level means a wider confidence interval. If we do the same thing at a 99% confidence level, we'd get an even wider confidence interval. So again, it's like if we want to be more confident in our results, we give ourselves a bigger target to hit. Now, as we mentioned in the last section, with every formula we're going to get, there have to be some requirements that are met. We can't simply blindly plug numbers into any formula and expect to get a valid result. So to use these formulas for the margin of error and confidence intervals, first we must have a random sample. That's always going to be a requirement. If we don't have a random sample, we can't crunch the numbers enough to get a good result. Second, the conditions for the binomial distribution are satisfied. Now the important one there is that we have two events. In this case, a student either uses a credit card or they don't. Those are our two events. And then the third one is important. It says there are at least 5 successes and at least 5 failures. What that means in this case is that we have at least 5 people in our sample who use credit cards and at least 5 people who don't. This third one is important because it means that we've got to have a sample of at least 10 in order for this requirement to be met. If I have a sample of only 6, there's no way I can have 5 successes and 5 failures. So I've got to have a reasonable sample size. The next thing we need to talk about is determining sample size. Some people erroneously believe that the bigger your population is, the bigger your sample needs to be. That's not at all the case. So let's go back to this example of estimating the proportion of college students that use credit cards. In our original survey of 750 students, we saw that approximately 64% use credit cards. That was our sample proportion. At the 90% confidence level, calculated E to be 0.0288. That means we are in error by as much as 2.88 percentage points. Here we're trying to estimate the population proportion. 64% is an estimate. That error is by as much as 2.88 percentage points. Well, suppose we want to do better. Suppose we want a smaller margin of error. Or in other words, we want more accurate results. Well, the law of large numbers says that in order to get better results, I need a bigger sample size. So if I want a better result, I need to survey more students. Do I need to do 250 more students for a total of 1,000? Do I need to do 1,250 more students for a total of 2,000? Just how many more do I need to do in order to get a smaller margin of error? Well, let's restate our question in more precise terms. How many students must be surveyed in order to be 90% confident that the sample percentage is in error by no more than 1.5 percentage points? So here we want a smaller margin of error. Instead of 2.88 percentage points, we want 1.5 percentage points. So in terms of our variables, n equals what, so that e equals 0.015 at the 90% confidence level. Now remember, when we plug percentages into formulas, we always want to use their decimal equivalent. So the problem was stated in terms of 1.5 percentage points. That means e in a decimal is 0.015. So in order to do that, we're going to use this formula. This formula is just our formula for margin of error rewritten so that it's solved for n. And so here in this formula, we need e, which is our desired margin of error. That'll be given in the problem. P hat is an estimate of the population proportion P, and then Q hat is 1 minus P hat, and then Z sub alpha divided by 2 is our critical value corresponding to our confidence level. Yeah. Now, one important thing we want to note about this formula is that the population size does not matter. It doesn't matter if my population size is a few thousand or a few million or a few billion. It just doesn't matter. So bigger your population is does not mean you need a bigger sample size. Now I do have to add one qualifier here. If our population size is small, like only 1 or 2,000, then this formula will give you an overestimate for the actual sample size needed. But we won't get into that technicality. So in order to use this formula, we need to estimate P. And there are at least 3 ways that we can estimate it. First is to use a sample proportion from a previous study. which is what we have in this case. In this case, p hat is 0.64. The second is we could use knowledge of the circumstances. Maybe we're a banker and I say, well, based off my experience working with college students, about 60% of them use credit cards. So in that case, I'd use p hat as 0.6. Third, if I don't have any other way of estimating it, I'll just use p hat to be 0.5. Why 0.5? Well, because p is somewhere between 0 and 1. Take the value right in the middle, 0.5. Okay. So in that case, p hat is 0.5. That means q hat is 0.5. If I plug those values into my formula, I have n is z squared times 0.5 times 0.5 divided by e squared. 0.5 times 0.5 is 0.25. And so here we get a slightly simpler formula in the case where p hat is unknown. N is z squared times 0.25 divided by e squared. Okay. So going back to this example, we have p hat is 0.64. That comes from our previous study. So q hat is 0.36. E is 0.015. Again, remember we're using the decimal equivalent of 1.5 percentage points. Now at the 90% level, z sub alpha divided by 2 is 1.645. And so we plug our numbers in. 1.645 squared, 0.64, 0.36 divided by 0.015 squared. There on the right you see the calculator command. Now whenever we do margin or do sample size, we always want to round up to the next whole number. So we're going to round this up to 2,771. So in order to get this margin of error, I would have to survey at least 2,771 college students. Well, now let's do a similar example, but let's work at the 95% confidence level. So I want the sample size so that my sample proportion is error by no more than 1.5 percentage points at the 95% confidence level. Okay. Now our formula is the same. P hat, q hat, and e are all the same. The only difference here is that z sub alpha divided by 2 is 1.96. So I plug those numbers in and round off my result, and I get 3,934. So if I'm working at a higher confidence level, I need a bigger sample size. If I want to be more confident in my results, I need a bigger sample size. Now let's look at one last example of using confidence intervals. In a survey of 1,002 people, 701 said they voted in a recent presidential election. So in that sample, about 70% said they voted. However, voting records show that 61% of eligible voters actually did vote. So it looks like something's going wrong here. 70% of people said they voted, but actually 61% said they did. Let's use this information to find a 99% confidence interval estimate of the proportion of people who say they voted. So the first step here is to define the parameter. Now this is a step that the book does not do, but one that I think is important. When we define the parameter, we simply state what it is we're trying to estimate. In this case, p is a proportion of all people who say they voted. I stress the word all there because we're interested in the population of all people, not just the 1,002 in my sample. The first step. Second step is to define p hat. That comes from our data. So p hat would be the number who said they voted divided by the sample size, and that comes out to be about 0.7. Okay. The next step is to find our margin of error. And so here's our formula. P hat is 0.7, q hat is 0.3, n is 1,002. Critical value is 2.575 because we're working at the 99% confidence level. We plug those numbers into our calculator. We get a margin of error 0.0373. Next, we'll find our confidence interval. Here's our formula, p hat minus e, p hat plus e. We plug our numbers in. P hat is 0.7, e is 0.0373. And so here's our results. P is between 0.662 and 0.737. Now the last step is the most important one. We want to interpret it. Okay? So we are 99% confident that P, the proportion of all people who said they voted, is somewhere between 0.662 and 0.737. So note that 0.61 is not in the confidence interval. In fact, our lower confidence interval limit is quite a bit larger than 0.61. So that indicates that significantly more than 61% of people said they voted. So that means the survey results are not consistent with actual voter turnout. It appears that more people say they voted than who actually did. And that's common. People often give pollsters the answer that they think the pollster wants to hear as opposed to the true answer. Here they want to look like they're good citizens and vote, so they say they voted even when they didn't. Now this formula for confidence intervals is programmed into our calculator. We do not need to enter any data. We simply enter stat, tests, and then scroll down to option A. That's what we see there in the left picture. In the middle picture we have to enter X, which is our number of successes, N, which is our sample size, and then C level is the confidence level. Here number of successes would be the number of people who say they voted, which is 701. N is 1002. C level is 0.99. And then you hit calculate and you get the result that's shown there on the right. So that first line, you see the 1 proportion Z interval. That's the test that we're doing. And then you see the confidence interval, 0.6623 up to 0.73691. That's our confidence interval in the form of an interval, as opposed to inequalities like what we do doing paper and pencil. Below that you see p hat, which is just x divided by n, and then you see n below that. Now this command is called 1 proportion Z interval because we are calculating a confidence interval about 1 population proportion, and our critical value is a z-score. That's why it's given this name. Okay. Now one thing that this result does not give us directly or explicitly is the margin of error. Now I can find the margin of error if I'm given a confidence interval using these formulas here. I can also find p hat. P hat is the upper limit plus the lower limit divided by 2. And the idea there behind that formula is that p hat is right in the middle of my interval. E, I can find that by taking the upper limit minus the lower limit and divide by 2. And there the idea is that the overall width of the interval is 2 times the margin of error. And so take the width, divide by 2, I get the margin of error. That's it for this lesson. The Course Compass homework is titled Section 7.2.